Hello and welcome back to Quantum News Monthly, the show where we teach the science behind the biggest developments in quantum information science. I'm Debo.
And I'm Mingyu.
Last month, thousands of you tuned in to our discussion of the Harvard Logical Quantum Processor and why it's such a game changer. In this month's video, we will start by discussing this archive preprint that challenges some quantum advantage claims in the former paper.
Next, we'll ride the error correction bandwagon and talk about this theory paper published in Nature Physics that gives us a much more optimistic picture of the resources required for fault tolerance. Let's jump into it.
To discuss our first piece of news, let's quickly recap the Logical Quantum Processor paper from our January episode. In this paper that was published in Nature, the team led by scientists at Harvard demonstrated fault-tolerant logical quantum computation using up to 280 neutral atoms. Fault tolerance and error correction are important requirements of useful quantum computing, and Harvard's paper made huge progress in this direction. In the last video, we explained quantum error correction and compared Harvard's work to two other big players in the field, namely Google and Quantinuum, so check it out if you haven't yet.
And this month's discussion follows directly from the last part in Harvard's work, which is a realization of instantaneous quantum polynomial circuits, or IQP for short. IQP circuits may not have a lot of real-world utility, but they are hard to simulate on classical computers, which is why Harvard chose to simulate them. In fact, Harvard explained that these quantum circuits they ran are at the edge of what's possible on classical hardware. So their quantum processor must have caught up with advanced supercomputers, right?
Well, not quite. Just recently, an archive preprint was put out by scientists from IBM and IonQ, which showed that they could exactly simulate the circuit in 0.0025 seconds. That's a fraction of the time it takes to blink.
So what's happening here and why does it matter? That's the question, right?
Yeah, the whole point of developing quantum computers is that it provides an advantage over classical computers when solving certain problems. Classical computers, like these digital machines, have transformed the modern world, and they're probably never going away. But there are some problems or calculations that these computers just suck at, where quantum computers seem to be better, and that's because quantum computers can solve those problems in fewer steps. If we compare the time or computational costs to solve these problems, classical computers take exponentially more resources to solve larger problems. If I increase the problem size by 1, the computational cost can double. However, quantum computers can solve certain problems in polynomial time, which means that for really large problems, they can beat out classical computers. This would be the point of so-called quantum advantage.
Now, where this crossover happens depends on 1. The specific problem in question, 2. The specific quantum computing hardware, and 3. The algorithm available to solve it on classical computers. In fact, the situation can change as classical hardware and algorithms become more efficient, which moves the crossover point further out. This creates a bit of a moving goalpost situation as improvements to classical computing moves the crossover point further down the line. This is why the authors have called quantum advantage a continuous negotiation.
Cool. So the Harvard-led team chose the hypercube IQP problem because it is hard to simulate classically. They used 48 logical qubits to run the circuits, which includes hundreds of 2-qubit entangling gates. And they reported that as you increase the number of 2-qubit gate layers, the runtime to simulate this on classical hardware increases by a large factor. In this plot, you can see that the Harvard-led team estimated the runtime to increase egregiously when more 2-qubit layers are added to the circuit.
However, IBM and IonQ claimed in this preprint that they efficiently simulated the problem on classical hardware in just a few milliseconds. Not just that, they also ran the classical simulation for double the number of qubits and showed that adding extra gate layers did not increase the runtime much at all.
This does steal the thunder from the IQP quantum advantage claims a bit, but we have to say that the technology that the Harvard-led team has displayed is still very impressive overall. If you want to understand why, definitely watch our January episode.
Back to the preprint. The authors proved that by cleverly simulating this IQP problem, they can reduce the complexity from 2 to the n to 2 to the n over 3, which is a significant improvement because it's the difference between this and this. Furthermore, they also simulated that the runtime of this problem would be much lower, and it wouldn't grow so egregiously either. They did suggest a way to increase the complexity of the problem to 2 to the n by adding something called a permutation CNOT, which basically makes the quantum circuit more complex and harder to simulate classically. In fact, the original paper's co-author agrees that this can be done with current hardware so at least the 2 to the n complexity can be achieved.
Now, we've all learned a lot about the intricacies of quantum advantage from these conversations between the two teams. And this makes me appreciate even more the fact that science is falsifiable. You can provide evidence to refute a claim, so we can all help check each other's work. In fact, here's a few notable examples.
In 2019, Google came out with a claim to quantum supremacy for the first time, doing something on their quantum computer in 3 minutes, what they said would take 10,000 years on a supercomputer. Promptly after, IBM scientists came out saying, actually, this would only take 2.5 days. And then scientists in the Chinese Academy of Sciences said it would actually take a few dozen seconds only.
Also in June of 2023, IBM published a paper where they used their quantum computer to simulate something that was out of reach for current processors. But then, all of these papers claimed they could actually classically simulate this pretty efficiently. By the way, thanks to Dulwich Quantum on Twitter for compiling that list.
So science is really about going back and forth, and this is why we love science.
And we know that you love science, but science is hard, and we want to create a friendly learning community so we can all learn from each other. So please ask your science questions in the comments, and we'll go through every question on this video and answer them. Now, on to the next story.
So far, we discussed quantum advantage for sampling. But in order to achieve quantum advantage on a practical problem, we need a fault-tolerant, error-corrected quantum computer. This leads to our next piece of news: time-efficient, constant space overhead, fault-tolerant quantum computation. Holy crap, that's a lot of words. Let's just call it TechSoft. TechSoft.
Can we call it TechSoft QC?
TechSoft QC? Don't you like the sound of kts better? Okay, TechSoft QC.
In our previous episode of Quantum News Monthly, we learned a little about quantum error correction and why we need it. So those of you that haven't watched it yet, go check it out. But the basic idea is that in order to correct errors, you can use many physical qubits to encode each quantum bit of information, which we call the logical qubit. And by measuring their states in a special way, you can determine whether errors occurred and correct them, thereby protecting the logical qubit information.
But this is not the end of the story, because in the quantum world, unfortunately, all operations can have errors, even those special measurements for error correction. So, by trying to correct errors, you can actually have more places for errors to happen, and what's worse, these errors can spread to other physical qubits and become uncorrectable.
This is where fault-tolerant comes to the rescue. In short, you can use extra qubits and clever quantum circuit design to prevent the errors from spreading badly, or catch whenever errors happen.
So let's say we want to run circuits on W qubits. Let's imagine how to run the circuit fault-tolerantly. First, of course, you need physical qubits that make up the W logical qubits. And on top of that, you need many more extra qubits that are used to basically prevent errors from spreading badly. So you can see that there's an overhead for doing things fault-tolerantly. This is called the fault-tolerant space overhead, and it's defined as the ratio of the total number of required physical qubits to W.
It's like this. Let's say you're Elon Musk and you want to make a bunch of electric cars, but you can't do it alone. So you hire a lot of engineers to build them. The engineers are like physical qubits. But engineers can make mistakes and they keep getting into fights, so you need a whole crew of product managers and HR professionals to keep them doing the right thing. That's what fault tolerance is like. You have to pay an overhead.
Now our future goal is to run bigger circuits, so you need bigger codes with larger code distance. We explained code distance in our previous episode, so check it out. And the problem occurs when the space overhead also grows as you increase the code distance. This is like if you want to double the number of engineers at Tesla, you have to quadruple the number of product managers and HR. And that's terrible.
Joke, Jim. Got me go to the annex. No, God!
Unfortunately, in 2013, Daniel Gottesman showed that we can avert this crisis and have the space overhead approach a constant value, even if the code distance increases.
That means if you want to run a W-qubit circuit, no matter how small you want the logical error rate to be, the number of physical qubits required can be at most a constant number times W.
By the way, you can check out this video to learn more about QLDPC codes or quantum low-density parity check codes, which was the key ingredient of Gottesman's results.
But even with constant space overhead, there was a glaring problem that the community hadn't solved. And it wouldn't be solved for another decade. You see, when you run a quantum circuit consisting of d steps fault-tolerantly, you actually have to run a lot more than d gates to do it on the logical qubits. Not only that, you also need gates to find the errors, correct the errors, catch bad errors from spreading, and so on. The problem is that this starts taking a lot more time to run when you increase the number of steps d. And this is the time overhead. It's defined as a ratio of the total number of sequential steps to d.
In the 2013 paper by Gottesman, while the constant space overhead was achieved, the time overhead was still quite demanding. There were mainly two issues. First, the scheme was unable to run logical operations in parallel. And second, it is still unclear whether decoding of the quantum error correcting codes considered here can be performed quickly. So it's either super large space overhead or super large time overhead. And we have been kind of stuck in this problem for 10 years.
For 10 years, quantum information scientists searched for solutions to the space and time overhead problems to come up with efficient fault-tolerant design.
And then these two people, Yamasaki and Kwashi, came along and were like, have you tried combining different Hamming codes?
What are Hamming codes? And why do we want to combine them?
So up until this point, people were already combining error correction codes to increase the distance in a process called code concatenation. For example, you can kind of square this code to make this one with a bigger code distance. The nice thing about concatenation is that you can increase the code distance and therefore reduce the errors. But you pay a hefty price with these bigger codes because they need more physical qubits per logical qubit, which means a bigger space overhead. So simply combining codes together doesn't fix our problems.
The key innovation by Yamasaki and Kowashi is combining different codes from a family of codes called the Hamming code.
Say codes quickly 3 more times.
Codes, codes, codes. Hamming codes have been around for a very long time for classical error correction, and there's a quantum version of it too. Its simplicity helps in a lot of ways. The authors basically figured out everything from parallelizing logical gates to decoding efficiently. And most importantly, by combining different Hamming codes in this clever, layered manner, they avoided the problem of having fewer physical qubits per logical qubit. This led to an awesome fault-tolerant protocol that achieves constant space overhead and nearly constant time overhead at the same time. So this is a real breakthrough for fault-tolerant quantum computing. Just take a second to think of all the trial and error that scientists must have gone through to solve this complicated problem and get both constant space and almost constant time overhead. It's amazing.
But you also might be wondering, so what is this constant number you're talking about? And exactly how many qubits do we need for a fault-tolerant quantum computer? Well, according to this paper, the constant factor in the space overhead is about 1163. That means if you want to run a 1000 qubit circuit fault-tolerantly, you need 1,000,000 physical qubits. Not too bad, huh?
You kidding me? That sounds pretty bad. How the heck am I gonna get 1,000,000 qubits?
Well, if you think about the schemes we had before, this overhead would be way worse, especially if you wanted to solve more complex problems. I'm just saying, 1000 times overhead is amazing compared to 1,000,000 times overhead.
Yeah, that's true. It's important to remember that just 25 years ago, very few people thought quantum computing could work. Yet, we've come so far with hardware and theory. So we can accomplish a lot in the next 25 years if we tackle these other tough challenges one at a time. I'm sure there will be tons more scientific breakthroughs to come, and we'll be here to cover it.
So that's it for this month, and make sure to post your questions in the comments and we will answer them all.
And subscribe so you don't miss out our next video.
See you next month.